So in sections 8.5 and 8.6, we are going to take a look at functions that show exponential growth and exponential decay. So before we get into some equations, what I wanted to do is play a clip from the movie Pay It Forward, so you get a little bit of a better idea of what exponential growth is. So first, you're going to watch the very short clip where the idea is described.
Pay it forward. I know you want me to go. I'll go. What's paying it forward?
That's me. And that's 3 people. And I'm going to help them. But it has to be something really big. Something they can't do by themselves. So I do it for them. Then they do it for 3 other people. That's 9. And 3 more.
That's 20. Said it, so I'm not really good at math, but it gets big really fast. You know?
So in the movie, you hear the one of the actors say, "I'm not really good at math, but it gets quickly really fast." And that's the idea behind exponential growth. So far, we've been only learning linear growth, where, with every step, if you go to the right one, you go up 3, right one up 3, right one up 3. So the rate at which you're increasing is constant. Now with exponential growth, it's going to keep growing with every step. So, oops. So the little boy draws this on the board. So he has one person. Oops. Okay, so the little boy draws this on the board. So you have one person who does a good deed. And then he's going to help, or he wants to do a good deed, and he's going to help 3 people. And then each one of those people is going to help 3 more people. And then each one of those people is going to help 3 more people. So basically what's going to happen, the number with in every step gets tripled. So first you have only one person. So this is your step 0. Then we have 3 people, that's our step 1. Then we have 9 people, that's our step 2. Then we're going to have 27 people, that's our step 3. And basically the trend is that every time we keep multiplying by 3. So that's what exponential growth is. And the 2 most important numbers in exponential growth are your initial values. So at step 0, what was the initial value? And also, what are you multiplying by? Are you multiplying by 3 or by 2? So in this example, the equation would be, for this exponential function, y is equal to 1 times 3 to the power of x. And that's not x. Okay. So this is an example of an exponential function, and it's always going to have the same format. This is going to be the 0 value, and this is going to be the growth factor. So how fast are you growing? Are you multiplying by 3 or something else? So the 3 goes in here, and then the 1, that was your step 0, goes in here. So that's how you get exponential function. And the reason why the first number is always step 0, because think about what happens when you replace the exponent with 0. Anything to the 0 power comes out to be 1, so the answer will always be the coefficient, so this value here. So that's why the initial value is always going to be this number here. Okay, so more specifically, in our book, they break this up a little more. So they describe what an exponential function is, and it's pretty much a function that has this form, so it doesn't really tell you a whole lot, but it's still helpful. So linear functions were functions that we've seen so far. This is when, for every one to the right, you go 3 up. Every one to the right, you go 3 up. But we saw something similar. We had our 0 value here, and then our growth was here, right? So every time we went up 3, and that's where there was the slope, and when x was 0, this was our y-intercept. So this is very similar. So our 0 value is this right here, the first number, and then our growth factor, in this case we're tripling also, is this right here. Okay, so you're going to learn how to do different things. You're going to be able to graph them. You're going to be able to look at the table and write your own functions, look at the graph and write your own functions. So we'll definitely be able to do many things with this. Okay, so first you are going to write a rule for this function. So before we write the rule for the function, you want to make sure it's exponential. Just because it's in this section doesn't necessarily mean it's exponential, so we better check. So what we want to do is we want to take a look at what's happening here. What is our growth rate? So we go from 2 to 4, we doubled. We went from 4 to 8, we doubled, and we doubled. So this looks like it's exponential growth because all of these are going to be increased by 1. So we need 2 things from here. We need our growth rate, which we got, and we also need our 0 value. So when x is 0, we started with 8. So our rule for the function is going to be, and this is just notation saying f is the function that depends on x, because x is going to be our exponent. So our 0 value is going to go in the front, so it's 8 times, and then our growth factor, which is 2, is going to go here. So it's 8 times 2 to the power of x. And you can do it if you have some extra time. You can always check by plugging in one of these values. So for example, if I plug in 2, I want to make sure that my answer comes out to be 32. So 8 times 4 is 32, so I know that my function is correct. For part B, I also want to make sure that it's exponential growth. So over here we're tripling. And this looks good. And again, we need our 0 value, which is in this case is 27. So we'll start with 27. And then our growth rate is 3 to the power of x. So that's going to be our function. Okay, so now we're going to graph it, and I'm going to show you 2 different ways to graph it. So the first way is to use the idea of the 0 value and the growth rate. So first of all, you want to think about what is the number in front of 2x if we don't see it. So hopefully you realize it's 1. So this is our 0 value. So when x is 0, our y value is 1. And then if this is 2, that means that my y value needs to keep being multiplied by 2. So if my y value is 1 here, it's going to be 2 here. And then if I go in one more to the right, it's going to double again, so it's going to become a 4. And if I go to the right one more, it's going to double again, so it's going to become 8. Now if I'm moving to the right, I'm doubling. If I'm moving to the left, it's going to have the opposite trend, so instead of being multiplied by 2, it's going to be divided by 2. So it's going to go from 1 to a half, and then if I do half of a half, it's a quarter. And what's going to happen is your number is never going to reach 0, but it's going to keep getting really, really, really tiny. So if you don't believe me, if you type in 2 to the negative 100 on your calculator, you'll see that the answer is not negative, it's just a very, very small number. Okay, so this is one method, is to use this initial 0 value and the growth rate. You can also use a table, and that's what you'll see in our textbook, so I want to make sure that you're familiar with both. So if you just want to use a table, and I apologize, it's not very straight, but all you're really going to do is you're going to plug in some x values, and you always want to do some negative, like so 0, 1, 2, and then negative 1, negative 2, so that always helps. So when you plug in negative 2, you get 2 to the negative 2, which is 1/4, so this will be 1/4. You plug in negative 1, you get 1/2. You plug in a 0, and 2 to the 0 is 1. And when I say plug it in, you just plug it into the equation that was given to you. And if you plug in 1, you get 2 as an answer. And then when you plug in 2, you get 4 as an answer. Okay, so here we have to graph two things. We're going to have this blue function, and then we'll do this red function. Okay, so I'm going to use the idea of the zero value and doubling and things like that, because it's a little quicker. If you want to use a table, feel free to do that. So my starting value here is 3. And then the base is 2, so what that tells me is that I should double. So 3 times 2 gives me 6, so this will be 6. The next value would be 12, but I don't have enough space to go here. So if I multiply by 2 going to the right, I'm going to divide by 2 going to the left. So if this was 3, this will be 1.5. And then 1.5 divided by 2 is going to be 0.75, so it's right here. So it's going to look like this. And then for my red one, my initial value is -3. And my base is also 2, so I'm going to double. So if you double -3, it becomes -6. And then if I'm going to the left, I'm going to do half. So half of 3 is so half of -3 is -1.5. And half of -1.5 is -0.75. So this is what my graph is going to look like. And we're not going to worry about comparing it to 2 to the x, so we just want to grab these two. So this one is y is equal to -3 times 2 to the x, and the one on the top is y is equal to 3 times 2 to the x. And again, if you feel more comfortable using a table, you could certainly do that. It takes a little bit more time, but feel free to do that. Okay. So then the last section in this chapter deals with growth, decay, and it's exactly the same idea. So what I wanted to do is first take an example. So pretend you have, not pretend, but let's say you have a piece of paper, right, that has an area of 200, right, because 10 by 20 units squared. So then what I'm going to do is I'm going to fold this paper in half. So now it's going to look like this, right? So my paper is still 10 wide, but instead of being 20 long, it's going to be now 10 long. So my new area is going to be 100. So what I'm going to do is I'm going to fold it again. And it's also still going to be 10 units wide, but now it's going to be 5 wide, or 5 long, so it'll be 50. Alright, so take a look at my area. It goes from 200 to 100 to 50, so it's actually being multiplied by half. So this is an example of exponential decay. So it's exactly the same idea. The difference is that instead of growing, it's actually getting smaller. So it's getting either halved, or you could do a third or fourth or fifth, but the numbers are actually getting smaller. So in this example, if you want to write a function that represents the area in terms of folds, so x will be number of folds. It's exactly the same that we did before. Our very initial area is 200, right? So if you have 0 folds, if you don't have any folds, it's 200. And then I'm multiplying by 1/2, so my base is 1/2, and it's to the power of x. So that's really it. So there's not a big difference. The only difference is that now it's multiplied by half. Okay, so here's our first example from this section. First, we asked to tell whether it is exponential function. So first, take a look at the x's, make sure that they go up consistently, which they do. And then we're going to take a look at the y's. So what's happening here? It's a little easier to see here. I multiplied by 3, I multiplied by 3, I multiplied by 3. So yes, it's an exponential growth because it's getting greater. So the rule for the function, again, is going to use the 0 value and the growth rate. So my function is going to be 1/3 times 3 to the x. And that's it. So 3 came from the growth factor and 1/3 came from the 0 step. So now for part B, first let's take a look at the x's. We added a 1, we added a 1, we added 1. And then for the y's, it went from 4 to 1, from 1 to 1/4. So we're multiplying by 1/4. So my rule is going to be 1 times 1/4 to the power of x. So this would be an example of exponential growth, and then this would be an example of exponential decay. Okay, so, we're almost done here. So you have to graph a function. So we're going to use the same idea as before. My 0 value is 1, so I start here. And then 1/2 is the growth rate. So when I go from this to x being 1, I need to multiply my y value by 1/2. So it goes from 1 to 1/2. And then 1/2 will go to 1/4. And then 1/4 will go to 1/8. Now if I'm multiplying by 1/2, then if I go left, I need to divide by 1/2. Or another way of looking at dividing by 1/2 is going to be multiplying by 2. Right, so then this would be 2, and then this would be 4, and this will be 8. Now we could double check. So if 8 multiplied by 1/2 gives you 4, 4 divided by 1/2 gives you 2, 2 divided by 1/2 gives you 1, 1 divided by 1/2 gives you 1/2, and so on. So this is what it's going to look like. And here they ask us to state the domain and range. So remember, domain listed the x values and range listed the y values. For the domain, you can go all the way to the right or all the way to the left. So we're using all real numbers. And then for the range, it's a little different because we're only using the y values that are above the x-axis. So it will be y is greater than 0. You'll never be able to actually be equal to 0, but you can get really, really small. So it's all the y values that are bigger than 0. And this is going to be our last example before word problems. Okay, so first let's tell whether the graph represents exponential growth or decay. That's very easy. So growth means if I move to the right, from left to right, am I growing or am I getting smaller? So in A, as you move from left to right, your y values are getting larger. So this is going to be an exponential growth. And in this case, this is an exponential decay because as you move from left to right, it's shrinking, it's getting smaller. Okay, and then write a rule for the function. So you really just need two things. You need to know what's my 0 value and then what's my growth rate. So I'm going to set it up. Okay, so first let's take a look at 0 value. Here, when x is 0, y is 10, so this will be 10. For this function, when x is 0, y is 8, so this will be 8. So then I need to know my growth factor. So how did I go from 10 to 12? Remember that I took my 10, I multiplied it by something, by this rate, and I got 12 as my answer. So if I divide both sides by 10, my growth rate is going to be 12 over 10, and we're going to simplify that to 6 over 5. So this will be 6 over 5. And here, this is a little easier because you went from an 8 to a 4. So clearly we multiply by half. If you don't see that, you could say 8 multiplied by this rate gave me 4 as an answer. And if you divide by 8, you get the same 1/2. So that's it.